Hi students, good morning everybody. In the previous lecture, we have seen vector equation of a plane passing through the given point and parallel to given vectors. Now today we are going to see the vector equation of a plane passing through three non-collinear points. So let's see theorem. The vector equation of plane passing through non-collinear points A with position vector A bar, B with position vector B bar, and C with position vector C bar is R bar minus A bar. It's dot with B bar minus A bar cross C bar minus A bar is equal to 0. So let's see the proof of this theorem. See, we have a plane which passes through three non-collinear points, A with position vector A bar, B with position vector B bar, and C with position vector C bar. So see, we have a plane this plane which passes through 3 points. Point A with position vector A bar, here it is B with position vector B bar, and this point C is here with position vector C bar. If we join AB, AC, so we have these 3 points. Let point P with position vector R bar be any point on the plane passing through non-collinear points A with A bar, B with B bar, and C with C bar. So see, point P is here with position vector R bar. If we join AP, so this is R bar. Stop. See, from the figure, see AP bar, AB bar, and AC bar. See, AP bar, AB bar, and AC bar, these 3 vectors lies in the same plane, so they are coplanar vectors. So AP bar, AB bar, and AC bar are coplanar. Means they lies in the same plane. Now AB bar and AC bar lies in the same plane. So AB bar cross AC bar. AB bar cross AC bar is the vector which is perpendicular to this plane. So AB bar cross AC bar is like this. So here if we draw, then this vector is AB bar cross AC bar, and this is perpendicular to the plane. So this is AB bar cross AC bar. So AP bar, AB bar and AC bar are coplanar vectors. So therefore we have AP bar, its dot with AB bar cross AC bar is equal to 0. AP bar, as AP bar, AB bar and AC bar are coplanar vectors. So AP bar dot AB bar cross AC bar is equal to 0, because see, AB bar cross AC bar is the vector which is perpendicular to the plane. So it is perpendicular to AP bar. As AB bar cross AC bar is perpendicular to the plane, AP bar lies in this plane. So AB bar cross AC bar and AP bar are perpendicular vectors. So their dot product is 0. Now, by using the definition of position vector, what is AP bar? It is nothing but position vector of the point P, that is R bar, minus position vector of the point A, that is A bar. R bar minus A bar, its dot with AB bar. What is AB bar? B bar minus A bar cross AC bar, C bar minus A bar is equal to 0. R bar minus A bar dot B bar minus A bar cross C bar minus A bar is equal to 0. And by the definition of scalar triple product or box product, this is nothing but the box product of three vectors, R bar minus A bar, B bar minus A bar and C bar minus A bar. So this is nothing but R bar minus A bar, B bar minus A bar, C bar minus A bar is equal to 0. So this is the vector equation of a plane passing through three non-collinear points A, B, C. So this is the required equation of plane. Required equation of plane means equation of plane passing through three non-collinear points. Now remark, see, this is the vector equation of plane passing through three non-collinear points. So it's Cartesian equation. The Cartesian equation of plane passing through non-collinear points A, x1, y1, z1, point B having coordinates x2, y2, z2, and point C having coordinates x3, y3, z3 is determinant x minus x1, y minus y1, z minus z1, x2 minus x1, y2 minus y1, z2 minus z1. Third row, x3 minus x1, y3 minus y1 and z3 minus z1. This determinant is equal to 0. So this is the Cartesian equation of a plane passing through three non-collinear points. So let's see another type. So normal form means the equation of plane in normal form. Theorem. The equation of plane at a distance p unit. The equation of plane at a distance p unit from the origin and to and to which unit vector n cap is normal. Is r bar dot n cap is equal to p. So the vector equation of plane in normal form, that is the equation of plane at a distance p unit from the origin and to which unit vector n cap is normal, means to this plane the normal is n cap, or n cap is the unit vector which lies along the normal. So see, this is three-dimensional system. So this is your required plane, which is at a distance p unit from the origin. This is origin O, x-axis, y-axis, z-axis. So if this point is n, then this length of this ON is P. So let's see the proof of this theorem. Let ON is perpendicular to the plane as ON is perpendicular to the plane, so plane is at a distance p unit from the origin, so therefore length of ON is equal to P. Length of ON is equal to P. But in this statement of the theorem, one thing is given that n cap is the unit vector along the normal. As now here normal is ON, so as n cap is unit vector along normal, means n cap is unit vector along ON also. You may write here ON also, because normal is ON, vector along ON, because normal is ON. This is perpendicular to the plane. So n cap is the unit vector along the normal. Normal is ON, so ON bar is equal to P into n cap, because magnitude of ON means length of segment ON is P. If we multiply this length by unit vector, we get a vector along ON. So ON bar is equal to P into n cap. Let point P with position vector r bar be any point on the plane. Suppose your point P is here with position vector r bar. If we join this OP, your point P is here, this is P. Now see, ON is perpendicular to the plane, NP lies in the plane, so ON is perpendicular to NP. Along ON there is unit vector n cap, so n cap is perpendicular to the NP, means NP bar is perpendicular to n cap. NP bar is perpendicular to n cap. As we know that as any two vectors are perpendicular, then their dot product is 0. So NP bar dot n cap is equal to 0. Means, or you may write it here also, NP bar. You know that by using the definition of position vector, NP bar is nothing but position vector of the point P. If you join this, this is your NP OP bar and it is R bar. So it is OP bar minus ON bar. Its dot which n cap is equal to 0. OP bar minus ON bar. But what is OP bar? That is position vector of the point P and it is R bar minus ON bar. We have ON bar is equal to P into n cap. P into n cap. Its dot with n cap is equal to 0. That is, now distribute this dot over subtraction. So it is R bar dot n cap minus P into n cap dot n cap is equal to 0. So R bar dot n cap minus. Now n cap is the unit vector and we know that we have the property of dot product. A bar is equal to magnitude of vector A square. Now n cap is unit vector. So n cap dot n cap is equal to magnitude of n cap bracket square. But you know that n cap is unit vector, so its magnitude is 1. So 1 square become 1. It means P into n cap dot n cap, that is P into 1, and it is equal to 0. So R bar dot n cap minus P is equal to 0. It means R bar dot n cap is equal to P. And this is the vector equation of plane which is at a distance P unit from the origin, and n cap is the unit vector along its normal. So let's see some remarks. See, now n cap in this type, n cap is the unit vector along the normal if L, M, N are direction cosines of normal to the plane. If L, M, N are direction cosines of a normal to the plane, n cap is the unit vector along its normal, then n cap is equal to L into I cap plus M into J cap plus N into K cap. This is first remark. If L, M, N are direction cosines of normal to the plane, then that n cap unit vector is equal to L I cap plus M J cap plus N K cap. Now if n is foot of the perpendicular, as we have seen in this figure, see here, this figure is like this. Just I will draw the rough figure. See, this is your normal to the plane and this is origin. So here, if this n cap is foot of the perpendicular, if n is foot of the perpendicular, drawn from origin to the plane, and the distance of that plane from the origin is, suppose P means length of ON is equal to P, then coordinates of N are coordinates of foot N are PL, PM, PN. So PL, PM, PN, these are the coordinates of foot of the perpendicular. Now third remark, the normal form of the Cartesian equation the normal form of Cartesian equation of plane is Lx plus My plus Nz is equal to P. Now here, what are Lmn? Lmn are direction cosines of a normal to the plane, and that plane is at a distance p unit from the origin. So its Cartesian equation is Lx plus My plus Nz is equal to P. Now next, fourth remark. There are two planes which are at a distance p unit. There are two planes which are at a distance p unit from the origin and having n cap as a unit vector along normal, comma, namely r bar dot n cap is equal to plus or minus p. Means here the fourth remarks gives us that there are two planes which are at a distance p unit from the origin and along its normal n cap is the unit vector. There are two planes, so this equation of these two planes are r bar dot n cap is equal to plus or minus p. Means one plane is r bar dot n cap is equal to plus p and other plane is r bar dot n cap is equal to minus p. So today we have taken the equation of plane passing through three non-collinear points, Cartesian equation of plane passing through three non-collinear points, and in this last type, the normal form of vector equation as well as normal form of Cartesian equation and their remarks. So in the next lecture we solve some examples on these types of equation of plane. So today we stop it here.